This is the FP1 paper from 2022. So the first question was about ellipses and hyperbolas. You have this sheet. I honestly don't think that anyone ever needs to learn either chapter 2 or 3 from the book, because this sheet tells you all of the answers. It tells you what E1 is. It's going to be b squared equals a squared into this, where a is 4 it looks like and b is 2. So we can shove those numbers in there. We'll get an expression for E1 eventually, which is this. And then here, hyperbola, same thing. We'll shove it into this expression, which is just the same, but with it backwards. And we don't know what a and b are in this case, but we can just leave it as that. Of course, we're told e1 times e2 is 1, so therefore e2 I think is 2 over root 3, which is there. We'll put that into there. It squares to 4 over 3, I believe. 4 over 3 minus 1 is 1/3, times both sides by 3, and you'll get to there easily enough. Good. Given also the foci ellipse are the same as the foci of the hyperbola, foci are here, they're just plus minus AE. Now, of course, these A's and E's are different. So let's just do the ellipse first, I guess. AE for the ellipse is 4, because that's what A is, times root 3 over 2. And AE for the hyperbola is, well, E is 2 over root 3, and A is just A, unknown. We can solve this for A, though, by doing some maths. And then, of course, we can put that A equation into, anything that we want to find the B one, I guess. You can put it into this one here, the one that you finished up with at the end here. So 3 squared is 9, divided by 3 is 3, and then b is, or b squared is 3, which is fine. That's all I need, because it wants me to write the equation of hyperbola. B squared is just 3, so I just put 3 in. A squared is 9, isn't it? Which I can write as 3 squared. You get something that looks a bit like this. It doesn't really matter. Good. Question number 2 is a early T-substitution question. Firstly, we just need to figure out that this is modeled each day after the first. So like the second would be, you'd put in x as 1, because that's the first day after the first. So we need to put in x as 30, I think, for this. So we just put x as 30 into there. Make sure it calculates in radians, because it says so, and you end up with this. Even if you miscounted the days here, you're told the answer here, so you can just adjust and pretend you got it right. Use the substitution in this. Now, usually T formulas look like this, and that leads to this and this. You're just allowed to write down those results. If we're using this, though, well, that's just with theta being x over 60. I think would get us there. So if theta is x over 60, we get t is tan x over 120, and then if we have theta is x over 60, we replace those in there. And I think these are the two things that we should be using. So okay, we put those things into, where do we put them? Sorry, we put them into here, of course, because that matches up nicely. So we put those into here, we get this. We can, of course, combine these two things together, same denominator. We can times this one by this over this to make the same denominator here as well. You eventually end up with that. I won't go through the maths too much. Hence determine the first day of 2029, when there will be at least 12 hours of daylight. So we're just going to take this, we're going to put 12 into it. That's the reason that T-substitution is great, is because it turns trig functions into polynomials. So we put 12 into here, and we times by 1 plus t squared. We do some maths, we solve this quadratic for this. And now remember, this is the substitution we made, so we need to undo the substitution and get x back. Now, we're looking for x to be a positive number, so doing t inverse of this, it might give us a negative. Even if it does give us a positive, it will be a positive that's much after the positive we get from this one. So let's just use tan inverse of this one here. I think that's the only one that really matters, since we're looking for the first day of 2029. Do tan inverse, times by 120, we get this. And now the hardest part of this entire FP1 A-level maths paper is working out what day of the year the 97th day is. This really took some work. January, I believe, has 31 days in it. However, you're only counting after the first day, so I think there's only 30 days to count, I think. 28 days in February, 31 in the next one, whatever month that is, and then another 30. We're well past 97 at this point, so what I just did was I firstly rounded that up to 98, because I interpreted this to mean that 97 won't have 12 hours, but 98 will. So I rounded up to 98, I took away this, this, and this to get to 9, and I interpreted that as the 9th of April as the answer. And that was one of the two answers they would accept, so I think I must have done it sort of right. But yeah, legitimately the hardest bit of this paper was that. Good. OB makes an angle of 45 with a positive x-axis. This is actually year 13 regular A-level maths. It's cosine angle thingies, where you have this idea. So the angle that you make with the x-axis is the x coordinate or x bit of the vector divided by the magnitude of the vector. So okay, x here is just 4, and the magnitude is 4 squared plus 2p squared plus 1 squared, and we apparently have an angle of 45. Cos of 45 is 1 over root 2. So if I just square everything, I'll make that into 1 over 2, and I'll square this and I'll square that, and then of course I can just solve this for p, and we'll end up with that, I believe. I hope so. So that's fine. And then we want to do this here. Cross product is when you transpose this and this into a matrix that looks like this. So it looks like this here with ij and k, and apparently that equals some multiple of this. Parallel means some multiple of that, which I've just denoted with a k. So okay, now we just do, well, for the I vector, it's going to be 2 times 1 minus 1 times 2p, so that's 2 plus 2p. For the j vector, it's going to be 2 times 1 minus 4, which is 6. But remember, there's always a minus here when you're doing determinant of this matrix, so that would be minus 6. Then k is going to be 4p minus 8, and just there. And now we can read across here. We know that minus 6 equals minus kp, which means 6 equals kp or pk. We know that 2 plus 2p equals 4. We can rearrange that maybe 4k and then put that k into here, and we can solve this for p. We'll get two answers, which will be these two, and all we need to do now is check the last one, which is 4p minus 8 equals 2k, where k is 6 over whatever p-value you want to use, of course. And you just shove in these two values and check which one works. So if I shove in 3 to this, this checks out because this makes a 4, and that also makes a 4, I believe. So that checks out. When you put a minus 4 into this doesn't work so well. And so p equals 3 is the only correct answer here. The area of the triangle, so for the area of a triangle, you just use the formula. So the cross product between two vectors is the area of the parallelogram, and of course, a parallelogram, or at least the magnitude, sorry, of the cross product is the area of the parallelogram. And the area of a triangle is just half of that. So we want to do half of the magnitude of this cross product equals 3 root 2. Of course, we can double everything. We already know this cross product. We did it on the previous slide. So we just want the magnitude of that, and which is going to be this, just the square root of these things squared. We could, of course, square both sides. 6 squared is 36, root 2 squared is 2, so that makes 72. We can sort this all out. It makes yet another quadratic that we just have to solve. We get this, and there's no reason that neither of these two answers are okay, are not good. I think they're both fine, because there's no reason that they shouldn't be. So we'll leave it there, and we'll get to question number 4. So this is just a system that it comes up in the book that you just sort of need to know. The first thing is that this is just a general formula given in y and x. We've been given v's and t's. You don't have to do anything to make them into y's and x's. You just use the formula with v's and t's in it instead. So that's the first thing to know. Secondly, 1 second, they want us to do 2 iterations in 1 second's time. So that means h needs to be 0.5, because 2 lots of 0.5 will give you 1. So that's going to be our h. And then we just need to evaluate dv by dt at 0. Initially we have t is 0, v is 0, so that's our sort of our x, that's our y in this sense. So we're going to say the next one is going to be minus the first one. The first one is just 0. And then dv by dt evaluated at this 0 thing here. So we put this 0 into here and evaluate dv by dt at that 0. And then we have this next one here. I don't think I really need this here, because I was just denoting that I'm doing the first one. Minus 0, because that's this one here, over 0.5, because we said, and then this just ends up being 10 times by 0.5 is 5, so we get v1 is 5, and that should be a 1 really here as well, because I've sorted out that n is 0 for this first one. That probably should just say 1. Apologies. And then we do it again, right? So we put in this 5 into here instead. We are finding v2 this time. We put 5 here as well, and then we still have h is 0.5. This makes something which you can do in a calculator, and you get v2 as that. Given that the acceleration initially is smaller than the current model, just make the 10 lesser. And I have made a note here, because the mark scheme said, keep it above 0, because if you make this 10 really like minus a million, I mean, any negative really, but if you make it a negative, look what happens to this first bit here. You put in a negative here, you times it by 0.5, you get a negative out of this, and that makes your initial v1, or your first v1 after the first iteration, a negative number, which suggests or implies that the rain is going upwards, which I don't think we can have. So just make it less than 10, but keep it above 0. It's going to be roughly the answer. So there's a second question here on conics, so we'll get out the cheat sheet just in case we need it. But I don't think we will. I'm just going to differentiate this using a bit of product and implicit differentiation. So differentiate the x to just a y, differentiate the y for an x dy by dx, leaving that alone. 36 differentiates nothing, just rearrange that. Put in the point that you've got, so put in 6 over t here and 6t here, and we get this. This t comes down here for t squared, the 6's cancel, we just get 1 over t squared. And then use y minus y1 equals mx minus x1. Put in this as the gradient, put in that as the y1 and that as the x1, and you get exactly what they wanted you to get, which is good. Then it says this, and find the equation of that, so you just do exactly the same thing again. So same thing here, then put in 3 over t and 12t into here, and you get this. You put it into the same thing we were doing before with the same sort of ideas. We get this, and so eventually we get to this, and that will be our second one. And now it says they meet at the point R. Show that as t varies, R is a rectangular hyperbola, so make it of the form this, or this really. Now all you have to do is get rid of the t's. So one way you could do this is I just immediately did, I think this one, no, first I think I times this one by 4, and then did this one take this one to get this. And then I think I just did this take away this to get this. And now, of course, what I can say is firstly the t's cancel here. And then I can just rearrange this for t, and then I can put it into there, and I end up with something that just has x's and y's in it, which ends up being this and this, which is of the form this, and so it's a rectangular hyperbola. Question number 6 is the easiest vectors question of all time. To turn 3 vectors into a plane, you just choose one of them to start with, so we'll just choose this one to be this one, and then b is just what do you have to do to get from here to here. So you have to add 2, add 3, take 9, and that will be b. And then c is what you have to do to get from here to here. So just choose the vector that you chose initially as your first one, and then you have to add 1, add 2, take 1, and that will be the 2 marks. Determine the coordinates of the points of intersection with the x-axis. So think about this in 2 dimensions. When do you intersect the x-axis? Well, you do it when y is 0. So in 3 dimensions, you intersect the x-axis when both y and z are 0. So we want the position of this vector, we want the y bit and the x bit to be 0, which is what I've just written down there. The y bit and the z bit, I think I just said, hopefully, I don't know. So okay, what I did I think here was double this one and do this plus this. So double this for an 8, this plus 8 is 6, double this for an 18, this plus this is minus 15, double this for a 2, add it to get nothing. Rearrange that to get this, or solve it, maybe I should really say, to get this. Put that into here, we get this. And then we just need to shove those 2 figures into our x row, and we have our x coordinate, which will be this, and our position will be that. Excellent. And question number 7 then. So we have this equation here, so this obviously is this one here, and then the line is just this. Show this thing here, well, it's tangent to the upside down bit of this. Now the upside down bit of this we can just write as minus x squared minus 8, because the mod function, if the thing inside the mod function is negative, which it is because it should be down here, then all the mod function does is times it by minus 1. So let's just times it by minus 1 and just set it equal to that. And of course if we just do this, we get this. And then it's tangent to it, right? It's tangent to this upside down curve. So b squared minus 4ac is 0, and we can just get b here, a here, c here, and it turns out to be the thing that we were trying to get. Given c equals 3m, so just replace c with 3m, and we can solve this for m very easily, and then of course we can just replace back in the c's. Now I thought this was actually pretty tricky. It says the value of m and c, so one of these 2 pairs is wrong, 412 or 824. Gut feeling says it's the 824. Because according to the picture, right, this is 8 here, because of this here, that's 8. So this feels like it's 12, just based on the picture, and 24 seems like it's too high, but it doesn't, that's not a proof. So what we could do instead is we could just substitute the point 824 into an equation that actually solves for the intersection. So let's say, okay, so again, this is the upside down quadratic, so this is just this quadratic upside down. When does that quadratic meet this line, 8x plus 24? And when you do that, you end up with x is minus 4, which then gives you that y is minus 8, if you just put minus 4 into the line. But that means that they're intersecting down here somewhere. And also this point here is, well, if you solve that, it's root 8, isn't it, this point here, which is lesser than minus 4. So the solution is over here, down here somewhere. And so what's actually happening is they're intersecting with the upside down part of the quadratic that doesn't actually exist down here somewhere. They're intersecting and tangenting down here, not up here. So we can ignore the 824 situation and just say the correct answer is 412 if we want them to tangent in the middle section like this, like it's saying. So that's that bit done. Hence solve this thing here. So all we need to do is say, okay, well the modi curve is above the line out here and out here, and it's equal to the line on this specific point here. So let's look for those points. Now, these 2 branches here are just where the curve is just x squared minus 8. So let's just solve x squared minus 8 equals 4x plus 12. Of course, we've got our figures now here. And we'll solve for these 2 intersections here. So 2 minus 2 root 6 is this one, and 2 plus 2 root 6 is this one. So we want to be less than or equal to 2 minus 2 root 6, or greater than or equal to 2 plus 2 root 6. But also, we can be equal to the line specifically here, when the upside down version, which is minus x squared minus 8, so just again timesing this mod function by minus 1 because it's upside down, is equal to 4x plus 12. We'll solve this and we'll get x is minus 2. And so it's also when x is minus 2 is our final bit as well. Good, so question number 8 is about Taylor series, so we'll get out her self for support. Use differentiation to show this thing. So I mean, 1 is here, so that means a is 1 is what we're using. We're going to use the function f of x as log x. Differentiate that for 1 over x. Differentiate again, this is x to the power minus 1, so the minus 1 comes down, bring it down to a minus 2. We get this. Let's evaluate all of those things at 1. So log of 1 is 0, 1 over 1 is 1. 1 to the power minus 2 is 1, bias that for a minus 1, and then we just put all this stuff into here. So f of x is f of a, which is 0, plus x minus a, which is 1, f dashed of 1, which is 1, so we end up with all this. I'm not going to bother too carefully, and we just end up with that, which is excellent. Hence prove this thing here. We'll just substitute for log of x your Taylor series for log of x, like you just found the Taylor series for a reason. So we get this, but now of course we can cancel this x minus 1 with this one, and this one of these with this one, and the next term is going to be an x minus 1 cubed, and is going to go down to an x minus 1 squared, which I've just said here. I don't care what the constant is. And of course, but when you limit as x goes to 1, this just goes away, this just goes away, every other term will go away because they're just higher powers of this, and we'll be left with 1 as our answer. Use the hospital to determine this thing here. Now the thing about hospital is it very loosely it says the limit as x goes to a of f over g is the limit of x goes to a of f dashed over g just, as long as the limit of f and the limit of g is both equal to 0 or both equal to plus or minus infinity, roughly. This is very briefly what it says. Now the problem is when we look at this is that if you call this f of x and this g of x just goes to 1 as x goes to 0 because it's not dependent on it, but g of x goes all over the place because this is a 0 and this I think is, oh no, it just goes to 0 I think because cosec, oh no, cosec is like infinity, so this is all wrong. So what we need to do is we need to rewrite this somehow to make it, do the thing that we want hospital to do. So clearly the best idea is to write cosec as sine 2x. I think if that's not the first thing you tried, I don't know what's wrong with you. So we have this, and now, of course, if we call f of x to sine 2x and g of x this, we can say, okay, well, as x goes to 0, this goes to 0, which is good. As x goes to 0, this goes to 3, but this goes to 0, so the whole thing goes to 0. So that's excellent. So we've got both things going to 0, which means this is a form that we can use. Let's differentiate both, and we get this for the first one, differentiate this, use a bit of product rule, I guess, and that goes differentiates to 1, that leaves alone, that leaves alone, that differentiates to 6x squared, 6x. And so I think this is the same as this here, just replacing both those things with their derivatives. And now as x goes to 0, cos goes to 1, so that's just going to go to a 2. This goes to 0, this goes to 3, and this, well, this is 1 over cos, but we've already decided cos goes to 1. So this is 1 over 1 times by 6. So I think this just goes to 2 over 3 times 6, which I think is 1/9, which will be our answer. And the very last question is about differential equations. So first we've got a substitution to make, so x equals ty. And if we differentiate this, dy by dt is, need some product rule here. Differentiate the t for just 1, so we leave the y alone. Leave the t alone, differentiate y for dy by dt. Differentiate this again, and the y goes to a dy by dt. Differentiate that, leave this alone, we get this. Leave this alone, differentiate that, we get this. And now let's just substitute these three guys into here. So we get t squared times this, which I'll write as 2 dy by dt, of course, because that's there. Minus 2t times this is there, plus 2x, and x is ty, plus this, where again x is ty, equals this. Now, when you expand this out, you're going to get a 2t squared here, which is going to cancel with this minus 2t squared there. So that's nice. And also, you can also notice that this minus 2ty will cancel with this plus 2ty, and then you're just left with t cubes in every term, so you just divide by t cubed, and you end up with this, which is great, because that's what they wanted you to get. And then you need to hence find a general solution, and okay, so let's pretend this is 0, and solve this with an auxiliary equation, so m squared plus 16 equals 0, that means m is plus or minus 4. You just need to remember that this means a cos 4t plus b sine 4t. If there was a real number here, that would just be e to the minus real number t in the front, but there isn't, so we just ignore it. We get this. That's the complementary function done, I think, now for the particular integral. We're just going to set up y equals lambda sine 2t, because that's of this form. Differentiate it for this, differentiate it again for this, because differential is negative sign. You put those three results in, or really those two results, don't need this one, into here, and you solve that lambda is a third, I should say. And then you put that third into here. You combine, of course, the general solution is the complementary function plus the particular integral. So we get this, the particular integral is this with a third in as lambda. So we get this. Last mark is just to remember that you're trying to solve the original differential equation, which is in terms of x's. So we just say x is ty, which means y is x over t, which means if I just replace this with x over t and then times everything by t, I'll end up with this, which will be the answer. Thanks for watching, and I'll see you next time.